on a two-dimensional universe, when we have all the x and y, we define the line by a point and a slope. Okay? Either we're using the point slope formula or equation or the slope intercept, which is again point and slope. When we define a line in the 3 dimension, we use a point on the line, and we use the vector direction of the line. Now, what do we mean by that? The line, I can take 2 points on the line and come up with a vector that will give me direction. But also, I can find another vector that starts at the origin, for instance, that is parallel to that line. Okay? But it has the same direction. Remember, a vector is a vector. It doesn't matter where is the initial point. I can put the initial point on the origin, or I can place it anywhere else in space, and it will be the same vector. This is what we call a free vector. There is, on the other hand, a vector that represent a point in space such that the point is connected to the origin. So we draw, for instance, a segment from the origin to a point in space. We create what we call a position vector. For instance, the point 3, 4, 5 in space, where x equals 3, y equals 5, and z equals 3, 4, 5. X equals 3, y equals 4, and z equals 5. I can say that this point correspond to the position vector 3i plus 4j plus 5k, right? This is a vector from the origin. So we're going to play with that as I explain how to derive an equation of a line in 3D. So let's write. We define a line L in 3D by 1, a point on the line, and we say this is a point P sub 0 with coordinate x sub 0, y sub 0, z sub 0. And later on we're going to translate it into a position vector r sub 0. And then 2, we're going to say the direction of the line L the direction of the line L, and given by what we call, given by a vector V that is parallel to the line L. I think I'll draw it, and this will illustrate what I'm talking about. So let's draw a coordinate system with x, y, and z like so. And in red, I'll draw a line in space at random. So let's say this is the line L. On the line, I'll pick up a point that will help me to define the equation on the line. So this will be point P0, with coordinate x sub 0, y sub 0, z sub 0, as people say, x naught, y naught, and z naught. Now, the corresponding position vector, as I said earlier, will be a vector from the origin. Let's say this is the origin O to the point. So this will be vector r sub 0. So r sub 0, the position vector, has x sub 0, y sub 0, and z sub 0, or x naught, y naught, z naught, as its component. It's a vector component. In addition, to help me with the direction of L, I'm going to pick up another vector parallel to L, like so, and this will be vector V. So vector V is parallel to the line L, and it will have a component A, B, C. And vector V gives me the direction of the line L. Now, I'll pick up a random point on the line, and this point will be P, not P sub 0, and the point will have the coordinate x, y, z. And I'll create another vector, vector r, another position vector, I should say, goes from the origin to this point. Okay, so r has the coordinate x, y, z. I'm sorry, has the component. The coordinate are the coordinate of the point, but the vector component of vector r is x, y, z. And now I'd like you to look at the vector that represent the line segment P sub 0 to P. Okay, so we're going to call this vector A, and it's this vector, this piece right there in between the 2 points. Okay, so this will be vector P. I'll draw it like so. Vector A. Vector A is P sub P naught P, like so. All right, but if you look very carefully of the vector V and R naught, either by constructing a parallelogram or moving vector R naught to the end of vector V in the opposite direction, notice that A will be V minus R naught. Actually, R, I'm looking at this, forget about V. R, it will be R minus R naught. Okay? Okay, imagine a parallelogram. So this is R naught. Negative R naught will be a vector in this direction. Okay, you connect the initial point of R naught initial point of R with the end point of negative R naught, and this will be R minus R naught, or R minus R sub 0. Okay, so this vector is this subtraction, is this difference. You don't see it? You want me to show you? No, that will be the magnitude. This is the vector notation. Okay. All right. Let me. I still this quiet is unsettling me. So let me show you. This is vector R, and this is R naught. This will be negative R naught. Okay. So therefore, this vector from here to here will be R minus R naught. Okay, which is equal to the one on top. Okay, I didn't draw it well. These two need to be parallel but in opposite direction. So let me make a minor query. I guess that's what Lizzie meant by shaking the paper or something. Okay, so you can see the same vector right here. So this is A, and this is A. Okay, hopefully now it makes sense. the outcome of this, the last statement, is the following. We're going to write, I'm going to solve for r, and I say r equal r sub 0, r naught plus a. All right. Now going back to the vector v. Remember, v is parallel to the line L. So now we're going to say that, however, A is parallel to V, right? So, but let's assume that V is a unit vector, but A is not necessarily a unit vector. So it has the same direction as V, but scale. Okay? So because they are parallel, we're going to say that A equals T times V, where T is a scalar multiplier of V. Okay? So the conclusion is we have one representation of this line as a vector. We're going to say that R will be the specific position vector, R sub 0, R naught, corresponding to that given point, P sub 0, plus some scalar T times the direction vector times a vector that is parallel to the line. And this is what we have here. Okay, now since P, which is a point x, y, z, varies along the line L, right? We can pick up any point on the line to present P, so we can say that this point varies along L. And what makes it vary? It varies with T. T is just a scalar multiplier. In fact, T is a parameter. Like we recall parametric equation of calculus 2. We're going to actually generate parametric equations here. So as T varies, for instance, if you look at this equation right there, okay, what happened when T equals 0? When T equals 0, then R equals R sub 0. We're back to that point. When T equals 1, then we'll have R equals R sub 0 plus another vector. When T equals -1, we'll go along the line but in the opposite direction. Okay, for instance, P, I can find out that T equals 1 corresponding to a point here, T equals 2 will be corresponding to another point further on the line to the right, but a negative T will bring it to the left of the point. Okay, but the point varies along L as T varies. Or another way to describe it is going to say that the line L is traced out by the endpoint or by the tip of vector R as T varies, which is the same thing as the earlier statement. Okay, so parametric equations. Of the line L. Okay. V, the vector V, we said has component A, B, C. Later on we call this the line or the direction numbers of the line L. And therefore T, V, this part of the equation is simply going to be TA comma TB comma TC. Okay, and continue, and we'll say that R, which is R sub 0, actually let's write before we go, let's remind ourselves that R sub 0 or R naught is the vector x sub 0, y sub 0, z sub 0. Okay, and therefore the vector R from here will be this sum. Plus this vector TA comma TB comma TC, or if we put it together we have this vector representation. It's not parametric yet, but it's as close to parametric as we get. X sub 0 plus TA, y sub 0 plus TB, and z sub 0 plus TC. This vector. Okay, this is and this will lead to the parametric equation. Since R equals x, y, z, let's do it on the next page. Since R is the vector, the position vector A, Y, Z, we have X equals X sub 0 plus AT, Y equals Y sub 0 plus BT, and Z equals Z sub 0 plus CT. Those are the parametric equations of the vector. Okay. So you have a set of three equations. If we solve for t, for the parameter t, we'll get what we call symmetric equation. Okay. Can I undo the split? All right. So the above are the PE, the parametric equation of the line L. Okay? Now, the next topic will be symmetric equation. Okay, and we obtain those by solving for t. So solving the parametric equations for t, then x equals x sub 0 plus at give you a solution t equals x minus x sub 0 over a, and likewise t equals y minus y sub 0 over b, and t equals z minus z sub 0 over c. Okay, so we have the following set of equation: x minus x sub 0 over a equals to y minus y sub 0 over b, and since all equal t, then z minus this equals also to z minus z sub 0 over c, and those are the symmetric equation of the line L. Okay, so we call those the above are the symmetric equations of L. So in summary, if I put everything together, then we have three representation of a line in space, in a three-dimensional space. The one will be the vector representation of the line, which you can see it here, or you can see it here explicitly. I'm sorry, yeah. Okay? These two are the same. The second is the parametric equation of the line, and the third is the symmetric equation of the line. So a vector representation, parametric representation, parametric equation representation, and symmetric equation representation of a line. And now we need to practice some.